Then here we go. Right. So yeah. So this week lab, next week chapter 42 and chapter 44, and then in the final week, the week of the 21st, we'll just have the one class on Friday where we'll do a review. And like I was saying, because we're kind of getting into the last two chapters fairly late, there's probably just gonna be like one question from each on the final. There's probably gonna be more questions from like relativity, from like the chapter 40 stuff from the first midterm, maybe 2 or 3 questions from the second midterm, since it's kind of we already done it not so long ago, so not too much emphasis on that. But if we look at the course outline, um, basically, yeah, I talked about chapter 41 for Wednesday, and so next week, I'll put up stuff for chapter 42 and 44. I'm gonna straight up tell you that the biggest stuff we'll do for the tutorials is the Bohr's model of the hydrogen atom. So that's like the energy levels of hydrogen. It's probably the most important stuff. So it's probably a big hint as to what I'll ask you. For the nuclear structure stuff, probably most important thing will be the nuclear binding energy and radioactivity and the decay process. So that's the type of decays like beta decay, alpha decay, and gamma decay, as well as decay process. So this is, have you ever heard of the word carbon dating? That's when you look at how much of a sample is left, and based on the half-life of that material, you can figure out how old the object you're looking at is. So we'll look at that, and I'll also, there won't be any more assignments to hand in after assignment 4, but I'll probably put up, like a quote unquote assignment 5 that's not to hand in, it's not for marks, but just a series of questions on the topics that did not get a chance to be on an assignment. So just maybe a few questions from 41, 42, and 44 that are likely to be, similar to what I could ask you on the final for those last 3 chapters. Yeah. What else? I feel like that's pretty much it. So yeah, last week I fortunately got a bit of a seasonal cold. I lost my voice. I literally could not talk without breaking into a coughing fit. So I didn't really get the chance to record properly. So I still owe you the back end of chapter 40, the lectures for that. If you've already seen on the Omnivox, you do have the slides up there, but I'll put up my voiceover as well. There's already the stuff for chapter 41. And what else do I want to say? Oh, yes, I think most of you saw the assignment already, but teacher evaluations are up on the Omnivox. So please fill that out and get that back to the college before the end of the course. It's very useful for me and the college to have that feedback on paper so that, given the following semesters, following years, I know what worked, what didn't work, and thus I'm gonna keep improving the way we do this course. But in the meantime, I am still your teacher for the next few weeks, so please feel free to come forwards to me and with any questions you have or anything you want to clarify or explain, and I'm always happy to help. Don't wait till putting everything on the review form to let me know something I missed. Here to help you. So I also got getting questions about the second chapter 39 tutorial. And what happened with the second tutorial on relativity, that got taken down by YouTube. I can't find the video, so I'm trying to recover it. In the meantime, what I did was I put up the slides from the second tutorial on Omnivox with notes on them telling you what the solutions to each question was. and I put up I found the audio recording, so like the audio only version of our second tutorial. I found that, and I also uploaded that to Omnivox. It's MP3 format, so you can just play that in anything. So it's not exactly the ideal solution, but at least you can go over the slides with the audio recording and just kind of hear me talking about the solutions. And that's all. That's all the announcements. So without further ado, I'm just going to jump into our tutorial today and talk about chapter 41. I don't get to, put memes on all my slides because I don't want to seem like I'm trying to be hip, but I'm particularly proud of this one. So chapter 41 can be a bit of a mind bender because we're now getting to see the true nature of particles that really doesn't really affect us in the everyday world, but when you start examining subatomic particles, you do have to consider a full quantum mechanics description of them to measure certain properties. And as such, you can't talk about kinematics anymore, velocity, acceleration, position, those sort of functions that we've done. We even done it in this course when we talked about simple harmonic motion. They don't really apply to quantum particles anymore. They are just not applicable because there's always some uncertainty to some particle's position anyways. So rather than talking about a function that describes a particle position, we can only really have this function that describes where a particle can be based on a probability. And this is taking advantage of the fact that all particles have wave properties. So this function is actually called a wave function. And I just had a question. So the second midterm, I'm going to grade it today. So you can expect the grades and the solutions to be up online soon. So we already seen what we call wave functions. Remember when we talked about waves on a string, how you could describe kind of like a sinusoidal wave using a cosine function or a sine function. When we talked about oscillators, we also talked about a particle, a mass on a spring. You could describe the movement and the position of it with a sine function because it just kept moving in a cycle. So for a quantum particle, you can describe where it can be found using the wave function. And again, it's not like it's not describing a physical thing, but rather probability where it can be found, where in space you can find the particle. So the function does have like a cyclical component. It can have sine and cos, but because it's not a physical measurement, the function is can be a bit more intricate, and thus in like a general form where the particle is unconstrained, you would have a formula where you have a real trigonometric function and a complex one. And essentially that allows you for more advanced descriptions of the state of the particle that you wouldn't quite have in a simple harmonic oscillator. This is quantum mechanics, so there's a lot more sort of details that you could cover. We won't talk about them in this course, but I'm just kind of laying the foundation for this for future physics lessons. Most importantly, the what's called the modulus, which is essentially the square root wave function, can be used to find the probability of finding the particle. So if you have a particle in a box and you open the box, what are the chances that the particle is in the lower corner? And that's based on the square root of the wave function here. The wave function is always using psi. And for the purpose of this course, the wave function is really just describing a single particle. So what it amounts to is that if you were to graph the wave function and you found the area under it, the size of the area are the chances of finding the particle in that region. And what this extends to then is that the area between 2 points A and B is probability of finding the particle in the region between points A and B. So the area under the curve, right? If you were to calculate the area under any curve, the general way to do this is with a integral. So this is the mathematical way of saying, give me the area under any curve. And you're not going to have to like solve integrals or anything, but we present it here because it's a general statement for what the area under the curve looks like in math language. But if your wave function, looks like a square, then you can just get the area. Maybe it's like a to b, and maybe goes to some value, a squared. So the area would be a squared, the height essentially, that's the amplitude squared, and then minus times the length, a minus b. So if you get the area as a square, and this represents the area under the wave function, then this area is the probability by definition. And there's a few conditions that make wave functions sort of legal or allowed, which is the fact that if the square of the wave function represents probability, then the entire possible area that a wave function covers has to be 1, essentially saying that the particle has to exist somewhere in space. So there's a 100% chance that you'll find it somewhere. So if you were to, find the area from negative infinity to infinity of the wave function under the wave function, you will get 100%. So probability, right, in math, we measure it from 0 to 1, so 0 to 100%. And this condition is called the normalization condition. And we will assume that all wave functions obey it, since the particle has to be found somewhere. Following that, we learned that in the real world, particles have constraints, and we made up a simple case where a particle is stuck in a box. It cannot leave the walls, it's inside. And when that happens, the wave function cannot be anything we want it to be. The wave function actually has to have sort of like nodes at each wall. So the wavelength of the wave function is such that it's gonna end at the walls. So there's only certain wavelengths that are possible, because the wave function has to be 0 at the wall. So this quantizes the waves that are possible. It's kind of like when we had standing waves. You can only have standing waves that had nodes in the on the ends of the wall. So only a possible series of harmonic wavelengths and frequencies were allowed to form inside the walls. You could only have standing waves with certain frequencies. It's the same thing with the particle in box. You can only have wave functions representing the particle with certain wavelengths. But the wave function, the wavelength of the wave function is related to the particle, since the particle has this like wave particle properties to it. It follows then that the wavelength of the wave representation of the particle is related to the particle's momentum. So if the wavelength for a particle in a box can only be a discrete set of wavelengths, and that's related to the momentum, then the momentum is also discrete. And it follows then that since the energy is proportional to the momentum of the particle, then the particle's energy is also discrete. It's quantized as well. There can only be some certain types of wavelengths that fit in the box. So there's only certain types of momentum and only certain types of energy. So we get to then define the ground state energy for a particle in a box in terms of the particle's mass and the size of the box, as well as a few extra terms like the Planck's constant here, h. But most importantly, what this is telling you is that any particle in the box has a ground state energy, and that is independent of any speed or anything. So that means that even if it's not moving, it has energy, it has this ground state energy. Sorry, let me say that again. In this example, the energy, because there's no potential energy inside the box, all the energy is just kinetic energy. So the first legal state for the particle is one with this ground state energy. So you can't have n is equal to 0. There's no n0 state. This is the lowest state a particle can have. And inside the box, all its energy is kinetic energy. So that means that the lowest energy state is non-zero. The particle then must have kinetic energy. It must then be moving. It must then not be at rest. But for all intents and purposes, just like this formula here is probably this kind of stuff probably ask questions on, as well as the quantized momentum and wavelength, but they're all related.
Sir?
Yeah.
Like for that equation, like is there like a like max energy level allowed, or like is there only like a lowest energy equation?
So there's okay. So let's for the that's a good question. So quantum mechanics by itself, yeah, it would allow it. There's no upper limit on energy. However, if you include relativity, yes, there is an upper limit set by relativity because eventually the particle will start moving to the speed of light. But just quantum mechanics alone, without bringing that in, no upper limit.
But what would that equation look like for a like the highest energy allowed?
Well, you what sets the energy levels apart really is this term here that accounts for the quantum state. So the ground state corresponds to n is equal to 1, and any state after that is, a bigger number. It's a quantum level that keeps going up. So if theoretically there's no limit, then the highest quantum level is infinity. But again, we're talking about like purely theoretical. So eventually, as you increase quantum levels, you get to like some infinitely high state where n is essentially infinity, and since the energy is proportional to the square of your quantum level, then your energy essentially would reach infinitely high.
Which is like impossible.
It's physically impossible, yeah.
Okay, thank you.
But again, asterisk on that because quantum mechanics by itself actually allows infinite energy. Like in fact, if you look at the walls, if you look at the walls of the box, the walls have an infinite potential. So they're like an infinitely tall mountain that nothing can climb. But in the real world, there's also relativity, which sets a limit to how fast things can go. So that relativity plus quantum mechanics doesn't then allow infinite energies, but quantum mechanics by itself does. But anyways, quantum relativity is like a whole other ball game. It's wild. Okay, yeah. So I thought I do a few questions. Maybe I'll give you some time to do this one, but I'll give you a hint. So we want to find the kinetic energy of a baseball. So we can actually use quantum equations with real world objects, because the wave function can actually be used to describe not just one particle, but a system of particles. And what is a baseball if not a bunch of particles put together into a system? So it is fair game, though the results tend to just be in agreement with classical mechanics. So we don't bother with complicated quantum equations to using them in the real world, because real world kinematics are more than enough. But we will for this question. So kinetic energy of a baseball. And we're told that it's confined to a one-dimensional box that is 25 centimeters wide, and the baseball can be treated as a wave in the ground state. So we're asking for kinetic energy, and you're assuming that the baseball then it's kind of like worked into this model of the particle in the box. So it's energy which it's asking for, it's being on the ground state. So you can just kind of figure out what the ground state energy needs to be. And for the formula, then you have h squared, you have a factor of 8, you have m, and you have L squared. I'll give you like a minute to see what you get. We really know everything. So you circled B, you're correct. Since if you plug everything in, you have like 0.25 centimeters squared here. Sorry, that's already meters. So you'll end up with 16 h squared divided by 8, which is 2h squared. So Planck's constant is like 6 to the power of 10 to the negative 34. Planck's constant is tiny, real tiny. So what this is saying is that a baseball at the lowest energy state has energy, kinetic energy equal to 2 times the square of a super tiny number. So tiny, right, that like it's approximately just 0. So yeah, even though quantum mechanics says that, yeah, particles are not ever at rest, even at their default state, they have some energy. In the real world, right, the ground state of anything, that energy that they have is so tiny that it's 0. Nothing looks like it's moving. So I've got a question about Planck's constant. So Planck's constant is essentially a term that does show up a lot in quantum mechanics, and The official number for it is 6.626 times 10 to the negative 34 joules per second. Sorry, joules times seconds. And Planck's constant is a very useful and common value in quantum mechanics. It was originally determined by Maxwell Planck while studying black body radiation, where he determined that the energy of the black body radiation was actually proportional to some integer multiple of the frequency. So there was a direct relationship between energy and frequency, and thus in a functional form, then there had to be some constant of proportionality between them. So he just called that constant h. So basically, whatever frequency you had times some constant of proportionality gave you the energy of black body radiation. And through experiments where people were able to measure the frequency of radiation as well as its intensity and therefore its energy, they were able to find what the relationship was between energy and frequency. And that relationship then was based on this proportion, this constant h, where a big amount of frequency will give you a tiny amount of energy. So Planck's constant basically exists to relate basically what Planck's constant is about is the fact that everything in the world has wave-particle duality, and everything has energy, and that energy is actually related to the wave frequency of whatever object or particle we're looking at. So Planck's constant h is about that relationship between the energy of a system and the frequency of its wave representation. So it's probably like, I'm saying, like, if somebody wants to get like a tattoo of physics constants, Planck's constant will probably be like in the top 5 next to the speed of light. Also, you may have seen some formulas using h with like a bar like this. This is just Planck's constant divided by 2 pi. It's just used sometimes to make some equations look cleaner. But this is still a constant. This is still, this divided by 2 pi, so it's like 1 times 10 to the negative 34. Also, one thing I haven't really talked about is the fact that, like, what happens if you use the uncertainty principle in the real world, right? If you try to measure, the like the length of a baseball, how well can you know its momentum based on the uncertainty principle, which is what I drew here. So let's say, yeah, you measure the baseball on with like on like a meter stick. So you measure that it's like, I don't know, like say it's 10 centimeters, and your accuracy, the uncertainty of your ruler being a meter stick might just be 1 centimeter, or a tenth of a meter, or a hundredth of a meter. So the limit on how well you can know the particle, the limit of how well you can know the particle's momentum, according to quantum mechanics, you can determine that by the uncertainty principle. So the lowest accuracy to which you can measure the baseball's momentum would be h divided by 4 pi times delta x, which is again the accuracy of your ruler, of your meter stick. But again, h is tiny constant. So we have 10 to the negative 34 divided by 4 pi, which is like, roughly 12, times x, which is like 0.01. So This is roughly 5 times 10 to the negative 32. So that's like your resolution limit to how well you can measure your baseball's momentum. Clearly, this doesn't matter because whatever speedometer or like laser detector or whatever you use to measure how fast the baseball's going, its resolution is going to be much. Its accuracy is never going to be as tiny as this. So this hard limit set upon us by the uncertainty principle, by quantum mechanics, doesn't really bother us in the real world because our instruments are much less accurate and precise than this tiny number. So there's probably going to be a question on the final, or like you might probably be asked to like make us compare why a formula works for quantum mechanics, but why we won't use it for in the real world. And then we're like, well, because the results are so small that it doesn't matter. So this question here, I'm asking what the ground state of a particle and minimum value of momentum. So for momentum, now that we're talking about a particle in a one-dimensional box, so that's telling you that it's in this wall. So I'm talking about the minimum value of the momentum. So minimum value is a key word because the momentum is essentially related to the energy. So minimum value implies ground state basically, because momentum can only get bigger from there, from that state. So the ground state momentum is also related to the wavelength. We know that for a particle in the box, the wavelength is some kind of like harmonic wavelength. The ground state is n is equal to 1, so that's when the wavelength is twice the length of the box. It just kind of looks like an eyebrow, like the first harmonic. So in this case, momentum is related to wavelength by the formula, by the de Broglie formula, h over momentum. So momentum is equal to h over lambda. And so lambda in this case is just 2L, so it's h over 2L. L is the length of the box. So if you plug everything in, we said L is 1. We should get this should get you 3.3 times 10 to the negative 34. So I had a question about using the formula h squared divided by 8ml squared. So this formula represents the quantized energy. So what we want to look for this question is the momentum. So rather than using a formula for quantized energy, use a formula for quantized momentum, which would be wait. That's worth pointing out that if you find the energy for a particle, you can get its momentum, because recall the relationship. For a particle in a box, we said that all the energy is kinetic energy. And one way of writing the kinetic energy formula is to write it as momentum squared divided by 2m. So if we plug that in, we get n squared, h squared, 8m, l squared is equal to p squared over 2m. And if you solve for momentum, you're gonna end up with this formula. Okay. So this is asking about the second excited state of a particle in the box. So it's the same box because it's the same length, and it's the same Actually, the mass doesn't matter. We're told it's the same box as the last question. And so we already knew that it's ground state momentum. So for its ground state momentum was what 3.3% for negative 34. So now you're looking for the second excited state. So the second excited state is actually n is equal to 3 because n equal to is the first excited state. So recall that the general formula is always H2L n. So in other words, the second excited state is just the ground state momentum times 3, which would be just 9.9. You see. What is the quantum number n of a particle of mass m confined to one-dimensional box when its energy is such and such? Also, I had a question about why is n is equal to 3. So again, the n right represents a quantum level. So because n is an integer from 1 to 2, 3, 4, 5, 6, infinity, that means that the smallest value of n is the ground state. So anything above the ground state is an excited state. So the one that comes next is the first excited state. N is equal to 2. And then the second excited state will be one up from that. N is equal to 3, and so on. Anyway, so in this question, we're just looking for the quantum number for a particle with some energy. Because we already know the energy, we can just say, well, that's for some mystery quantum number. But we also know that this came from the general formula, right? This came from plugging in n, which was already known, to the formula, which was what is it, h squared over 8 ml squared n squared. So clearly they've gone from this to this by plugging in n. And it must mean then that, you can just kind of, all the constants here don't really matter. Just kind of comes down to the fact that we somehow went from having n squared over 8 to having 2 on one side. So clearly we need to do some math to isolate for n. So n squared must be multiply 8 by both sides. We get 16. Take the square root of that, n was 4. So we were in the third excited state, which gave us the energy that we got. Cool. So the wave function for a particle in a one-dimensional box is given such. Which statement is correct? Okay. Give me like a minute to think about this one. I think the one you think is right, and then I'll discuss it. Okay, so A says that the wave function gives the probability of finding the particle. That's not true. What gives probability is the modulus of the wave function, but not exactly, not directly. By itself, what statement B says, that the modulus gives the probability, but that's not quite right. The square is actually the probability density. It's the area under it that gives you probability. So by itself, it's not a probability, it's a density. C says that, yeah, you take the probability density times a sort of small size of a region, it'll tell you the probability of finding the particle between some point and sort of that interval. And this is correct. So that's by definition, if you have a density, you times it by a volume, it gives you the volume. And because of the probability density, it'll give you a probability. Part D says that this thing here, this is basically looking at the area under the wave function from 0 to L, gives you a probability, but that's not true. It's only when you look at the area under the square of the wave function that you'll get a probability. So that's not right. E, the integral looks more correct. It's looking at the area under the square of the wave function, but it's telling you that tells you probability between finding the particle between x and delta x. But if you look at this two numbers, that tells you the size of the region. It goes from 0 to L. That means that you're looking at the probability of finding the particle between 0 and L. So it's would be correct if it told you the probability of finding the particle between 0 L, but it's not what it says, so it's incorrect. Okay, for the purposes of time, just talk about this one. So physical reasonable wave function, by definition, it needs to be defined at all points in space, because it's, talking about a particle where it can be and cannot be. It has to be continuous and single valued. So the answer for that would be D. And again, the reason for these conditions, don't worry about it too much, but basically the wave function, because it's describing a physical particle, it has to make sense. So you can have more than one volume in one point. So wave function of a particle in the box of length L is given by the function here. Which of the following positions has the highest probability of finding the particle? Okay, so note that these answers, x gets bigger as you go down their answers, because x is now a bigger fraction of the length. Highest probability implies that you're more likely to find the particle there, and to find the probability, you will need to look at the square value of the wave function. So square that first, and then we have n pi xl. So this function, the square, is related to probability. So it's a function of some constant and a function of the sine square. So whichever value, whatever you plug into here, the sine square, the bigger the output, the bigger the probability, right? Because this is related to probability. In other words, probability would then be proportional to whatever you get from the sine squared function. So the bigger this, the sine square is, the bigger the probability of finding the particle at that x. So the biggest one is, if you compare the different answers, you can plug in here. If you plug in, n pi and any number times x. So I'm just gonna make up a new constant, call it al for and so this becomes sine squared n pi times A. And we have for options A, B, and C, basically A would be 0.33, or for option B would be 0.4, or for option C, A would be 0.6. And basically, to get the biggest probability, we want to make sign as big as it can be. So we should pick the bigger number, which would be option C. Okay. So here we're shown a wave function, and the particle is confined between -2 meters and 2 meters. So the particle is stuck inside under the wave function. If you look at the amplitude, it flattens afterwards. So we cannot find the function here. We cannot ever find the particle here or here. It can only ever be found in between -2 and 2. And we need to find what the normalization constant is. So normalization constant ensures that the area under the square of the wave function is 1. So not the wave function, but its square. So if we were to graph the square of the wave function, then it would look similar, but the square of the wave function would have, right, if the wave function is just, a times some function of x, then the square of it, the probability density would be, a squared. In this case, where the wave function is defined, its square is also defined in the same region. So the square of the wave function would still be defined from -2 to 2, but now rather than having a as the amplitude, it will have a squared. So the normalization condition is that the total area under the square of the wave function is equal to 1. So this whole area, for it to be normalized, needs to equal 1. And if you notice, this is just a rectangle, eh? This is just a rectangle of like, spanning a length of 4. And its height goes up to a squared. A is just a constant. So the area is just the area of a rectangle, 4 times the height being just a squared in this case. But we know by normalization, the total area under wave function squared has to equal 1. So we just need to find what the normalization constant A needs to be. We need to solve for A. So bit of algebra here, divide by 4, take the square root. A is in the positive y-axis, so it should be positive. We take a square root of 1/4, we'll get 1/2. And that's all we have to do. The next question asks the same thing, but now the wave function is actually negative. The constant is now in the negative y-axis. So you think, wait, what about but isn't the probability density positive? Yeah, that's right. That's why the probability density, we always take like the square of the wave function, so it makes everything positive. So if you were to just square that to get the probability density, it would kind of flip to the positive y-axis. So in this case, it still follows the same idea that the area has to be equal to 1. So 4 times a squared is equal to 1. But in this case, the constant is on a negative axis, so you're probably going to want to it's going to be -1/2, right? This position is -1/2. It's on the negative y-axis. So yeah, that's all you need to do. So you don't have to do these questions using integrals. You can just use, classical areas of shapes to do them. Don't expect you to do integrals, but you should know, the normalization condition, area has to be 1 under the wave function squared. Last question. We're now given the probability density. So we already have the function we need, and we need to find the value of the constant to meet the normalization condition. So this is the curve we want. The area under this needs to be equal to 1. So this is a triangle of length 6, and its height is a square. So its area has to equal 1. So we say, okay, then the area of this triangle has to equal 1. The area of a triangle is always 1/2 its length times its height. So it's going to be 1/2 a length of 6 and a height, which is a squared, which gives you 3a squared. But we also know that the area, because this is a probability density, the total area has to be equal to 1. So we solve for a, and we get the square root 1/3, and then we take the square root of that. We get 1 over square root of 3. And because there's an ambiguity here where a is a can be negative or positive in this case, because either way when you square it you get a positive number, so it doesn't really matter. So you can leave the a as either positive or negative. Both answers are valid in this case. Anyways, so yes, so I know this chapter is like pretty theory heavy, but as far as calculations go, the kind of stuff we've seen today is kind of like what I would expect you to do. Don't worry too much about fully grasping the full significance of Schrodinger's formula. You're not going to have to deal with that on the final. I haven't talked much about Erwin Schrödinger, but he's also the one responsible for the infamous, you may have heard about Schrödinger's cat. I'll tell you about that later, because it's a whole thought experiment that really puts a twist on things, and I don't want to add more convolution to this chapter, so I'll talk about it some other time. It's a good thought experiment. It's just maybe a little too much for now. But yeah, it's 10:55, so if nobody if you have questions, let me know. Otherwise, I'm gonna let you go so you have some time for your next class to have a little break, a little snack. So yeah, if you now have no questions, feel free to take off, and I wish you all a good day, and we'll see you at the lab on Friday. Oh yeah, you too, guys. Take care.
Thank you.
You're welcome. Question about the rest of chapter 40. I'm gonna upload the recordings today. It's worth pointing out for chapter 40, I'll probably mostly be asking questions on the stuff that has like a formula to it. So Compton scattering, photoelectric effect, Wien's law, Stephen laws, and the uncertainty principle. So more of a focus on that than the more esoteric theory heavy stuff. Anyways, if you have more questions, let me know. You can send me an email. Always happy to answer that. Otherwise, I'm just gonna take off, get more water. All right, everyone.
Sir, can I ask a question? I wanted to ask about twin paradox. What exactly questions can you ask us? Because I understand the concept of how like the person in the space cannot measure because they have an acceleration, but the person on Earth, because our constant velocity, their acceleration is 0, they can measure as a reference. But why
okay. The twin paradox?
Yes. What kind of questions would come from that?
Honestly, there's not much you can ask about the twin paradox. except a discussion of the problem itself, because the twin paradox as a setup already, it doesn't follow the setup as, because there's like a non-inertial frame, right? There's the twin, and then the spaceship, that's a non-inertial frame. You can't really discuss it with, you can't really treat that as a relativity, as a special relativity problem in the first place. At best, you can treat it as a problem where you break it up into two halves. But I guess what I'm trying to say is any question related to the twin paradox would just be a typical relativity problem where, you just, rather than treating the trip one, there and back as a single trip, which you can't under special relativity, you will just consider it as two separate cases. The trip one way and then the trip back will just be two halves of a question. But what I'm saying is like nothing more than that. There's nothing really more to really be done with the twin paradox, because it's not a case of special relativity, it's a case of a non-inertial frame. So there's not really much else to deal with. Nothing that you couldn't handle from, nothing that you wouldn't be able to do from just, doing regular relativity questions.
Thank you, sir.
No worries.
Have a good day.
Oh, you too, thank you. Take care.